this computer. So you may know that you will have some portion of the lab in your final exam. So it might be 20% to 30%. It will come from the lab, and the rest 70 to 80% will be from the course. So please do some practice on it. And if you are facing any problem with the labs, then you can just send me the email and the snapshot of the problem which you are facing, and then I'll try to resolve your problem either online, and if it was not possible online, then you can come to my lab. It is on the 10th floor of high tech building, and it's the 1008. So you can come to the lab and I can then help you with your problem, right? So before proceeding to the new work which we are going to do to perform today, let me go through the basics. So firstly, we generated a signal. So I'm not going into detail how we generated a signal because you already know how we did it. And after generating the signal to the Fourier series, then we sampled the signal and we took some portion of the signal. For instance, we took one and then we skipped some, and then again we took the other one and then we skipped some. So we took the sample of the signal. We didn't take the entire portion of the signal, and then we quantized it. We defined some quantization levels, and then we took some we assigned the quantized value also to the sample signal. And after that, we encoded the signal. Since we needed the signal to be in the digital form, so that's why we also converted the signal into the digital domain, into the digital form. And we use 4 digits for each quantization point. So quantized point. So each quantized point was assigned with 4 bits, and the leftmost was MSB. And then we used the BPSK modulation scheme. And the BPSK modulation scheme, we used two waveforms. So we were using the plus cos of 2 pi fc of TB, where TB was the bit duration, and for 1 bit, and if it was a 0 bit, then we were using the minus cos of that signal, which was 2 pi fc of TB. And then we transmitted the signal using the AWGN channel, and I also showed you what was the relationship of the signal to noise ratio and corresponding to the modulated signal that we transmitted. And when we had a high signal to noise ratio, then our signal was receiving at very low degradation. And when there was high signal to noise ratio, then the received signal was with a high degradation. So we also saw that in the previous lab. And this is the 10 that you see here. This is your SNR value. So you can increase or decrease this SNR value. If you decrease it, for example, to 5, it means that your noise power is increasing, then a denominator term is increasing, and the numerator, which is your signal term, it is decreasing. And that means that your noise term is dominating over your original signal, and then you have very distorted signal. So to have a very clean signal, you should have the signal to noise ratio as much as possible, which means that the numerator term should be much higher than the denominator term. And finally, we received our signal using the received filter. And after the receiving the signal, we converted the signal into frequency domain. I showed you how the story, how the signal was converted to the frequency domain, and then we discarded the unnecessary frequency which was belonging to the noise. So we discarded all those unnecessary signal, and after discarding those unnecessary signals or the unwanted signals, we were having only the original signal, the signal which was belonging to the what we desired. So finally, after filtering, we have done everything so far at the receiver side. So now we are in the receiver side. And receiver side, we are doing mostly the work that is reciprocal to what we had done at the transmitter side. So I'll first go to the drawing. I'll explain you how our new modules work. And Yeah, I think this is the last part of the end-to-end communication. So today we are going to recover the original signal that we had transmitted at the sender side. So let me switch the screen to the drawing, and I'll show you some basic concepts that we are going to cover today. And then I'll come back to this MATLAB, and then we will perform the today's task. So I'll make myself as a host on the other iPad. So make host. So you can see my screen, right? Can you see it?
Yes.
Yes. Okay, thank you. So I'll also give you some brief review for the previous work because we are doing something reciprocal of that. So we had defined TB, if you remember, in the previous lab, and this TB was the bed duration, and this bed duration was almost equal to 2 microseconds, right? If you remember it. And this TB contained 2 cycles. So it was plus cos. So if you see the sinusoidal signal, uh, this, for example, is your sinusoidal signal, and it is a sine signal if it starts from 0 and if it ends on 0 on 360-degree like that. And this is 180-degree and this is 0. Or if you are taking it in the radian form, then it is 0, then it is pi, and this is 2 pi. So it is starting from 0 when it is a sine signal, but when it is a cos signal, it is always starting from the like this, right? And I think like that. So the cycle is completed. So this is your cos signal, right? And this is your sine signal. So I hope you already know that. And we use the cos signal. So the cos signal was starting from, for example, like that, 1, 2. So we were using 2 cycles for each bit transmission. So if it was 1, we were using plus cos signal, which is this one, plus cos of 2 pi fc of tb, right? If you remember, we were using this one. And if it was the 0, then we were using a signal like that. And this was minus cos 2 pi fc of tb. So you already know fc was the carrier frequency. And you know how much was this one? So it was almost equal to 1 mega, not almost, it was exactly equal to 1 megahertz, right? And the TB was again your this bit duration, which was 2 microsecond. So the whole duration of each 2 cycle of the signal was 2 microsecond, and we were using 2 cycles for 1 bit transmission. So 0 was transmitted like this. So you had a sequence before this. Beforehand, you had a sequence which was coming from the encoding process. So encoding was giving you something like, I'm writing some random bits, right? 101111000011, something like that, to transmit each and every bit. For example, I'm going to transmit this one bit. It has to be superimposed over these 2 cycles, and these 2 cycles will, since it is 1, so it will be carried by this plus cos 2 pi fc of tb. But the next bit, which is 0, it has to be superimposed by the this one, and which is the minus 2 cos 2 pi of fc of tb, right? So this was how we were transmitting our signal. And once we transmitted this signal, then we had the AWGN channel. So the AWGN channel, it is a channel model, and it contained all the degrading phenomena that can happen to a signal. So the signal was distorted. The transmitted signal was, for example, like this. but you received some distortion on your signal, and it become a bit distorted. It became like that. So after the AWGN channel, we had a received filter. So in communication system, we call it the LNA, low noise amplifier. No, sorry, LNA is coming after that as amplifier, but it is not related to this one. It is coming after the filter. So firstly, you have to filter your signal. Filtering means that since your signal was degraded by your AWGN channel, and why it was degraded, as you remember in the previous story, I told you that there are lot of things in the path of your signal. So the channel is not clear. Your road is not always clear, but there could be some rough road coming, some rocks might be there, and things like that might be there, which is making your drive uncomfortable, right? So the same thing is happening to your signal. When you are transmitting your signal, there are trees, buildings, people, and lot of scattering things. So all those things, for example, walls or anything that is coming across the signal path, the signal is reflected off that obstruction, and then finally it received your signal, but the signal from the transmitter side is not coming directly to your receiver side. So if it is your receiver and this is your transmitter, they are not coming always like that. And if it is like this, for example, if it is the transmitter and the signal is coming directly to the receiver side, then it is called the line of sight communication. Usually for light communication or for the leader communication, we use this line of sight communication, but it's not always possible because you may have buildings. You may have buildings here, you may have trees here, you may have cars here, you may have people here. So many degrading factors are there, and your signal is reflected off this tree, then this car, then this building, and finally it is not only one copy of that signal, but couple of copy of that signal is impinging on your receiver. And then when many signals from your transmitter are receiving at your receiver, then they make your signal corrupted because of the multipath effect that I already told you. So this multipath effect makes your signal more corrupted, and because of this corruption and this signal not being received very accurately, we need some filter. And the filter, what the filter does, the filter is trying to remove this red things from here. It's not exactly removing it, but it's trying to mitigate it. Mitigate means that it's trying to reduce it as much as possible. So when you receive your signal, after that, after the filter, when you apply the filter, you receive a signal. If it was your received signal without filtering, and after applying the filter, you received a signal like maybe like that. So you are trying to remove this aggressive kind of fluctuation from there, and you see some smoothed version of that. So this smoothed version is possible because of the filter you have, and the filter has to be carefully chosen because sometimes you have this fluctuation important and you filter it out and you get a smoothed version for that one, which means that you are losing your information. This a little bit fluctuation was not noise, but the filter considered it as a noise. So here it was wrong filtering. So the filter has to be carefully chosen when you are doing some when you're communication engineers, then you have to carefully design the filter. And if you design a filter in such a way that you are taking out the meaningful information, it means that you are doing something wrong to your signal. It would have been better if it was without filtering. So please be careful. You have to be very careful with the filtering. And that's why we have a lot of filter types like the low pass filter, high pass filter, band pass filter. And then each filter have different types. So like Chebyshev filter and the Butterworth filter and then Kaiser-Wert filter, and a lot. There are a lot of filters. There are books on the filters. So it depends what kind of application you have and what kind of filtering you need. And based on that, you have to filter your signal. And let me also give you some very little details about the filtering process, and then I'll move forward to the it's not related, it's not very relevant, but let me give you a very little touch for the filter. For example, we are designing a low pass filter, right? So the response of the low pass filter is like this. Okay, so if it is your frequency axis, and this is magnitude of your signal, sorry, mag, natu, okay, whatever. So this is your filter response. Here, this one, this part is your cutoff frequency. So cutoff frequency means that ideally, any frequency which is lying in this range, it should be clearly passed, and right after the cutoff point, all the frequency should be suppressed. They should not be allowed to pass through. Now, there is a problem. We cannot have this kind of steep filter. Like ideally we need something like this, right? Like this should be very steep line, but it's not like this, but it is some inclined plane, something like that. It's like when you stop your signal, part of the unwanted signal is still transmitting, and finally after some time that signal is completely cut down. So this cutoff point is not working as very efficiently here. And if you want to make it more steeper like that, the blue one, then it means that you have to make it more expensive, or you have to put some more components there so that it can be more steeper. So then you have to put some more resources there, right? So the filter is not always this much straight away steeper. So one is this thing, the steepness of the filter. When you cut off, when you put the cutoff point, when you say stop, it should stop, but it doesn't stop at that point. It takes some time to stop, right? So the cutoff point is actually your stop alarm. Then there is the pass band. This is your pass band, and this is your stop band. So pass band means that here you want to allow any frequency component that is supposed to pass through, and stop band means that any frequency component which is lying in this portion, it should be stopped. It should be just cut off. But sometimes, as I told you, because of this response, some portion of this signal is interfering with that desired signal. So because of that, you still have, even after filtering, you have some of that components remaining there. So you still have some noise component there. So then there are, like, as I told you, Chebyshev filter or Butterworth filter or different type of filter, which has some strong features. For example, one filter will have a strong feature here. It will have a strong stop band, which means that it will not allow any unwanted signal to be interfere in this region. So that is a specific filter. Or some filters are more steeper. For example, they have more steeper response, and they have then that is another type of filter. And then some filters have less fluctuation in the pass band, then that is another type of filter. So depending upon your application of the filter, you can choose one, and then you can implement it in your communication model. Okay, so let's come back to the next process. After the filtering, we have the demodulation, which is our today's topic. So if we see the previous page, yeah, this one. So already this blue one, we know this, the one is carried by 2 pi fc of tb, right? So we are only using this kind of this intuition from here, and then we say that, let's say we have a cos of 2 pi fc of tb. So we know that this is supposed to carry the signal which is 1, not the signal, the bit which is 1, right? So we already know that this is carried by 1, and 0 is carried by minus, which we don't want at this point. So we say that any of our received bit, for example, we have a receiving bit. After the filtering, we will see that we will have 0 1 0 0 0 1 1 1 0 0 0, something like that. We will have a vector like that, and we say that this is our received bit, and we have to correlate it with this one. So I hope you already understand the correlation. So the correlation is like this. For example, you have two quantities, and one of the quantity is increasing like that. I'm trying to explain it in an easy way. And the other quantity is also increasing like that. So it means that one is also increasing and the other is also increasing. So the correlation is positive. Okay, there is a correlation and it is a positive correlation. So the maximum coefficient will be 1, and the no correlation means that there is 0. It has 0 correlation, which means that the one of the signal is increasing but other is like this. So it has no correlation because one is increasing but the other increase decrease increase decrease increase and something like that, and the other is increasing. So it means that there is no correlation at all. So which means that it's 0. Now, as I told you, we have a bit duration, right? So of 2 microsecond, 2 microsecond. And then our signal is like this for the, what we call it, for the 1 bit, which is plus cos 2 pi fc of TV. So it will have some point here, some point here, some point defined here, and it will have some points. And I think if I remember it correctly, it was around 20 to 21 points there. And all those points are like this. So you need some data for to correlate two quantities, right? So you have something like that. And then you are taking the portion of the signal which is belonging to, for example, the first bit which is received here. And this is defined. This you already know from the previous knowledge because you have plus cos 2 pi fc of TB, and something is here. So your signal, for example, for 0, it should be like that, and you will have some points like that. Now, if you take the correlation, this is at 90 degree, right? So something which is very high, and then it is declining to negative portion, and you will have some negative values. But if you look at this signal, here you can see that you have the very minus 90 degree, and then the signal is increasing, and then there. So if you look at both of them, they will have some negative kind of correlation. So the negative kind of correlation mean if you take the mean of the whole values that you receive from here, it will be less than 0.5. Okay, so this is one of the method which I used for recovering the signal. There are a lot of other methods too, but this is what I did. I will correlate the pre-existing defined signal with the received signal, and each and every point is correlated. And if it was one like that one, it will have a very strong correlation. Maybe some points are not that correlated, but you will receive a mean of 0.9 or something, which means that it is greater than 0.5 and it is 1. So we will correlate the signal which we already know, and the signal which we have received, and if its mean is greater than 0.5, then we will say that it is 1 bit. And if it means else, so this is if and this is else. So if it is mean is not greater than 0.5, if it is less than 0.5, it means that it is 0 bit. So this is how we recover our bits from the in this lab only. So in this lab we are recovering our bit from the modulated signal. So this is our demodulation process. So it is not only doing the demodulation, but alongside it is also doing the decoding. So if you clearly observe it, like it is not it is also giving us the 10100 and lot of bits in the vector form, right? So this is also our decoding process happening alongside with the demodulation. So again, recall that the modulation was, it was a high frequency signal, and we superimposed our low frequency signal over it so that our low frequency can reach to the destination with no extra resources involved, right? But at the receiver side, you have to recover your original signal from there. This is the original signal, which is this one. And this original signal is then converted into the bits form, which is the decoded form, right? So this is the this is the bit form. Now it's sorry, I just it is still not decoded, but you received the bit form. You extracted the bit from the modulated signal. Now we have to recover the bits from it. Once you have like 1011001101001, whatever it is, and then we had defined 4 bits for each signal. If you remember the encoding process, we had defined 4 bits, right? So, and the leftmost bit was the MSB, most significant bit. So this one would be LSB. So again, we will consider 4 bits, 4 bits, 4 bits, and so on. So 4 bits, and then we will convert it into equivalent digital form. Decimal form. So all the binary data is taken from the decoding process, and those decoding process will convert from the demodulation process. All the binary bits are taken from there, and in the decoding process, the equivalent binary is converted into the decimal form. Now we have the defined, for example, if it is the points of your signal, you have the for example, the decoded points here, and you have some number. For example, this number is 3, this is 4, this is 4, this is 5, this is 4, this is -2, this is for example -5, -5, -4, and this is -2 again, and this is 3, and then again 3. So something like that, you will receive the equivalent decimal form from the binary is this one. And now since this has been received, and then we will do one more process. We have to interpolate these points, and once we interpolate, which means that we have to connect these points in such a way that we recover the original signal from there. So this is how your interpolation will leads to your recovering your original signal, right? So this is all the story which we will be covering in today's lab, and this will be the end of the end-to-end communication. So you had transmitted something like this, and then you are receiving something like maybe like this or like that. So why is this still there will be some difference? Because your signal gone through a lot of processes. You modulated, you generated the signal, then you sampled it, then you quantized it, then you encoded it, and finally you transmitted it to some erratic channel. And then after the erratic channel, you again demodulated the signal, then you recovered the signal. And after recovering the signal, your signal looks something like this. So before the signal was like that, and after the signal was like that. So of course, there will be some degradation. That is not the, that is okay. The degradation is okay, but at least we should be able to receive all the information very accurately. So what we have transmitted, what we transmit should be equal to what we receive. Right? So the information, there should be no information loss. And if there is any information loss, for example, this is the high peak, but you are recovering it like that, it means that you are losing this information, this information, this information, this information, and that information, and that model is completely wrong. you cannot extract the information which were transmitted, right? So let's go to the MATLAB, and let's just do whatever I explained here. So I'll switch back to the other one. So I hope you can see my screen, right? Can you see my screen?
Yeah.
Okay, thank you. So let me start with the demodulation code. Demodulation process. So let me say that this is a variable DC data, and it should contain zeros equal to the bits we were dealing here. So what was the bits? I think it was bits, because we need something equal to the length of bits, right? So yeah, this one. So I will copy this one, and I'll say that zeros and the size of bits. So the and then I'll start again. So this process, as I told you, this is the correlation process now, and this is how we can recover our signal from the previous one. So I don't have to explain that again. So for k is equal to starting from 1 colon, then the jump is, you know, how much is the offset here, and the offset is TB. So it should be the bit duration, or the length of bit, and then we should go to the length of I forgot the variable, so we can go back to, I think it was T transmit or something. So from here I can see that one, sorry, not quantization bits, and after the, yeah, T underscore tran. So I should go up to this one. So I know what is my TB, and I should go up to the maximum of this one. So it is exactly something like that. So I'm using this line again. So length of this one, and let me finish it first. So I will end it before, and after, and then I will do something like a, let's say my variable is a, and I will use correlation coefficient. So this is the built-in MATLAB function. It will compute the correlation coefficient of the signal which we already know, and the signal that we receive, which is this one, for example. So the T-rays signal which we have just received, and it contains the signal, the 2 cycles for each bit, and the one which we already had transmitted. So I will say that cos of 2 multiplied by pi multiplied by 2 pi fc, which was 1 megahertz, and I think TB, yeah, TB. So this is the, or this predefined signal that we already know, and then I will take this signal which we already received, and we will take the correlation of this one, and this we received, so we have to consider it bit by bit. So like k is equal to 1 and then TB, right? So it will start from 1 and it will run up to T tran. So it will check for the entire length of the received signal. So T rays, so I should say k colon and then length of k plus length of TB, right? So it's I think it's exactly the same line that we used before. So length of TB minus 1. yeah, that's it. And then now I should declare a b variable, and it should take the mean of a, as I told you before why we need it. And then I should just put a condition here. Uh, if b is greater than or equal to 0.5, or simply say if b is greater than 0.5, so it means that it's not a, sorry, what is happening? This should be end. Okay, so if b is greater than 0.5, then I should say that this variable, and yeah, I should also, for example, L is equal to 1, I should start another variable there, and then I should say that um, this one of L, so this is the index now, so this of L is equal to 1. So only update the particular index there. Else, if it is not equal to 0.5, then again copy the same line, paste it, and 0. Is this clear? So this, keep doing it, and after the if condition is finished, after this if condition is finished, say that L is equal to L plus 1. So each time it should keep checking for this entire length of dB, and then it should be correlating these two, the received one and the predefined one. And if the mean is greater than 0.5, it means that it is 1. And if it is not greater than 0.5, then it means that it is 0. And then each time it should also increment the index of the decrement data, which we already defined there. So this is it. And then let's plot it. So FIGURE. Why I'm plotting it every time? Because there might be some problem with my code or something, so I can instantly know where the problem is. So I will say that this is the figure number 9, because the last figure I used is figure number 8, and the figure number 9 should be stem. I should use the stem as usual, and then I should use the decrement data, Control C. So it should again be looking like the one we already used before. And then let me plot it like that. It should show us only the what we call it, the binary bits. It should only plot that one, and grade on. And then I should just label it, the X label is it's the bit position, right? So I should say that position, and the Y label is the bit sequence, and the it should be something like bit sequence, and the receiver. Let's say versus transmitter, so that we can differentiate it from the previous one. Versus transmitter. So that is it. And yeah, let me just plot this one. I hope there shouldn't be any trouble. Yeah, there is. Correlation coefficient is undefined variable, and the spelling must be wrong. CORRCOEF. CORRCOEF, not E. So this is something which I have received now. Now, it should be, ideally, it should be exactly the same what we had transmitted. So you can compare it. If for your case, you should also plot this. Hold on, and you also plot it with the previous one with the different color, with the red one, and you can compare both. What is the difference between what we received and what we had transmitted, and then you will also see how much error in bit are occurred there, right? So now we see all the bit sequence that has been received. Now let's start with the decoding process. So the decoding is actually the binary to decimal conversion now in our case. So let me put a double this one. and DECODING. So the decoding process is, now if you look at this this one, this variable, if all the data is just in a single vector, or if I show you this one here, then you can see that the dimension is 1 cross 164, which means that there is one row and 164 column. So it looks like this. The data is looking like that. So it's in a single row. So I want it to be splitted into 4 bits, like 0 1 0 1, and then these 0 1 0 1 should come here, then the next should come here, and it should be equal to number of columns multiplied by, no, sorry, number of rows multiplied by 4 number of columns, because we defined 4 binary bits for each decimal, right? So let's reshape it first. So there is built-in reshape. So we can use that in the MATLAB, and let's do it. So again, I should say that let me not declare another variable for this, but I should make the changes in the same variable is equal to reshape. This is the reshape. So what you are reshaping? I'm reshaping the this one. I'm reshaping this one. And how are you reshaping it? I'm reshaping it in the 4 number of columns. And what should be the number of rows? So of course, the number of rows should be equal to the number of the this divided by 4, right? Since I'm using 4 number of columns, so the rows will be reduced by 4, right? So this is very natural. And this is how I did. And let's say I'm also taking the transpose of this so that I can see every column very clearly. And now if I run it, then I can see, sorry, error using must be an integer scalar. What does it mean? What does it mean? It should be an integer scalar. Let me take this one. RESHAP. I think it should be the length. It should be the length. Yeah, I got it. If I do it like LENGTH, because we need the length of it, not the entire. Yes, okay. So I got the problem. Length of this decimal data, and now I hope it should work. So let me run it. So this 1 cross 164 should be converted to 41 cross 4. So this you can see here, right? So now we have many columns, many rows. We have many rows and few columns. Now all these 4 digits should be belonging, or these 4 bits should be belonging to a specific decimal number. And the next 4 should also belonging to another decimal number, and so forth, so and so forth. Now my data is, I am already getting this binary data in the reshaped form, and now it's the time to convert it into the decimal form. So to do that, let me also make another variable. For example, RECV. For example, this is my RRECE, receive is equal to, I should say that zeros and equal to the size of, and I think we had declared another variable which was for quantization, this one. So I should it should be equal to MQ, receive it equal to the size of MQ. Okay, so we also have to compare it with this one. They should be also of the same size, because what we are doing here is exactly reciprocal to what we had done there in the transmitter side. So now I should use this variable mq receive is equal to so again not like this. So in the transmitter side we had used every fourth digit of the or how about I copy it from here? Let me copy it from here. I should use exactly the same thing with which we had done it here. So I think it was like this. All right, so I should use this one. Or this one. This one is much better. Anyway, it's similar. So I should use this one because I should use exactly the same 1/4. So this was 4, right? I think what I remember it was 4. Yeah. So it should start from 1 and it should jump because we have 4 digits, right? So it should jump from 4 and then the length of entire T. So I think the length of MQ, I should go make it MQ because so for each digit, it should, for each 4 digit, it should be able to define the equivalent decimal number. So you have to see it very carefully by yourself, and then you will understand it. And then I should use the binary to decimal, binary to DEC. This is the built-in MATLAB function. I think this is binary to decimal is BI to DE. And then I should say that the decimal data, and which is this one. And then the left is MSP, right? So I should say that left dash MSP. And this one. And if you remember, we had subtracted the minimum of the MQ just to raise the signal up, right? Why we were raising it up? Just to convert it into the binary form. But now we have to do the reverse process and we have to add that one, right? So add minimum of MQ, which we had done before. So something reciprocal. Before we had done minus of this one so that we raise up the signal and convert it into the binary form. And now we are doing something reciprocal to that one. And let's see what is there in the MQ receiver. So I can see some MQ underscore REC. So you can see that after 4 digit, I have 5, 5, 2, and something like that. So I have all the data ready, right? So if you want to plot it, you can, but it's not so good to plot it at this stage. So let's go and signal reconstruction, the final stage of the process. So signal reconstruction. So in the signal reconstruction, again I want to define the frequency axis for it, and since I want to apply some gain, which means that I'm also applying some amplification here. So amplification is required when your signal is very weak. Then in that case, you amplify the amplitude of your signal. And by amplifying the amplitude of your signal means that your signal become more strengthened and you can recover the information from there. So for that sake, I'm going to convert it first to the frequency domain, and it should be exactly the same way we did previously. So as you remember, we converted the into frequency domain in such a way that part of the signal was lying in the negative quadrant and part of the signal was lying in the positive quadrant. It was like from minus fs by 2 to plus fs by 2. So I hope you already remember that thing, and let's use it again. So I'm saying that my x-axis is sf freq is equal to -1 divided by twice of the sampling rate, let's say twice of the sampling underscore rate. I think this is the variable we defined before. Yes, so I'm using this one. So I'm starting from there, and then I am making the offset like this. Let's not make the offset, and then I'm going up to plus this one, right? So I'm starting from minus fs by 2 to plus fs by 2, and now I have to put an offset here. So when I'm putting an offset here, then 1 divided by, I'm saying that it is the sampling rate times what? It is the sampling rate times length of t, because we have to align it exactly with the time, right? So it should be like that. But now please remember, I had asked you previously that you have to sorry, there is one there. Previously I asked you that I'm subtracting something from here, but you have to understand that part, and I'm not sure if you have already done that part. So it is because since we are making the signal from minus fs by 2 to plus fs by 2, but there is 1 0 here which is extra. So technically if this was minus fs by 2 and plus fs by 2 but there was no 0, then it would be fine. But since there is one extra 0, so we have to subtract it from the final value. And that's why I asked you previously to check this, why I put this minus 1 over this term. So I have to also subtract one value from here because of the extra 0 that is in the middle, right? And yeah, it's okay now. And then now let me also convert this into the frequency domain. So how do I do it? Do you remember it? Anyone? No? So I have to take its first Fourier transform. Previously, when I was converting it, I took it first Fourier transform. So again, I have to take its first Fourier transform. So let's say f underscore receive is equal to FFT of, FFT is the built-in function that I have already used before. So this will convert the signal in the time domain into the frequency domain. And then this was my signal that was in the time domain. And if I want to plot the signal in the frequency domain, it's okay. And if you don't want to plot it, then still it's okay, because this signal is not so meaningful for you if you cannot understand it. But let's say we want to plot it. But before plotting it, I think I should also define a signal for the time domain. And this is equal to zeros and then size of the fres. I may need this variable later, so let me also do this colon and then sorry, not colon, semicolon and semicolon, so that I do not see it here. And you also for the semicolon here, because every time I'm seeing this L here. So again, also semicolon here and semicolon there. So it's important if you want to make your simulation faster. So this is figure 9, so I should plot it in the figure number 10. Okay, and at the figure number 10, I should say that plot, and freq is my x-axis, this one. This is my x-axis, and the y-axis is this one, but I cannot plot it directly because I have to shift it to the middle. So I will use the built-in MATLAB function, which is the FFT shift that I had used before. And then FFT shift will just shift this one. And also I can cross compare it with the message signal that I had there. I had transmitted from the transmitter. So I can also say that FREQ and the frequency domain signal of the uh, transmitted signal. So I can say that FFT of the MSG. Okay, so this is the frequency domain axis I just defined here, and this then I think this is not SST, it is the FFT, and also this is the FFT shift. So the message was this signal which I had defined here. So this is the message signal, right? And then after this, I should just grid on so that I can see the grid, and X label is my frequency domain. So I should say X label, and it is frequency FREQUENCY, and the Y label is the FFT message and FFT receive signal. So this is FFT of message and FFT of the received signal. And I can also differentiate it with the legend. So I hope you all already know these things now because we are frequently using it. So the first one is belonging to the bits, bit sequence and transmitter, bit sequence and receiver. This is bit sequence in the receiver, right? So this is bit sequence and receiver, and then the next one is the bit sequence in the transmitter. So the bits CQUE sequence and D and TX. So if I plot it, it should show me the both the pictures, right? So I think I should, so actually this is the time domain signal and the other is the frequency domain. So there is some mistake. We have to first convert the message signal into the frequency domain, and then we have to plot this and this one. So here I should first use the FFT of the message before plotting it. Now it will take the FFT of the message, and then it will FFT shift of the signal, and then it will plot it together. Now this is the FFT of the message. So you can see these fluctuation are all the errors that are happening, because in the transmitted sequence you can see this is the flat region and you only have the frequency component here, and then again the flat region. So we had couple of frequency component defined there, and then if I enlarge it, then you can see that still something is quite similar, but the other things are not fine. So all these things has to be removed. So to remove these things, I'll just add some line, but I'm not going to explain it. Just so please, you have to do it by yourself. You have to understand it by yourself, how I'm doing it. So if I see this one, for example, what is my range? So my range is starting from 20,000. Okay, so let me keep the maximum and minimum minus, and this is where is the figure? Sorry. So it means that the signal is plus 20 minus 20,000 here and plus 20,000 here range, right? So I have to discard some portion from here, and also I have to discard some portion from there. So let me do this here. So I think I already did that one. So I should say that Control V is F out, or F out of the freq. So inside the F out, this freq value is less than let's say minus 17,000, since my maximum is 17000, 20,000, right? So if it is less than this, R, F, Control C, and then again Control V, or if it is greater than plus 17,000. So if we are greater than those limits, then just ignore it. And then I should say that what is my received signal? Please, you have to understand where this one, this line that I'm writing it. Yes, you have a question?
What does that mean, error operation?
Sorry, I didn't understand. Can you please repeat?
In the last comment, there is the error operation.
You mean the error, right?
Yes, error.
I see. So,
161.
are you talking about the whole dimension now?
Oh,
So this one, let me, if I understood your question. Sorry, I should comment this because this is not
yes,
complete.
that's it.
Okay. Let me comment this one. Okay. Oops. Oh. Okay. So let me run this one. Oh, I think I have to bring the battery for the, yeah, just hold on. I'll just come. Okay. So if you look at this one, you can see that the bits and transmitter and the frequency domain, it looks like this. So each spike shows us a frequency term. But when we were transmitting it, we did some process. For example, we passed it through the AWGN channel, and AWGN channel added some further noise terms, and those noise terms are high frequency terms. So you can see those high frequency terms are those fluctuation and separate frequency fluctuation because it's in the frequency domain, right? So we have to remove or discard those things so that we can only see this portion of the signal. We can only see the clean version of the signal. So although still there will be some of the portion, for example, if we do it like this much time, right, or even this much time, but if we discard these aggressive kind of fluctuation from our signal, it seems like we can recover our signal in the real form, or in the with less degrading form. So is that the answer to your question? Or if there is anything, please ask it. Is that clear? Okay, thank you. So that's what I'm doing now. And then okay, so I did FRIC is less than 17,000 or FRIC is greater than the that. So then I have the FRACE, which is this one, and again the same condition. Okay, now I have to apply some gain here. So gain means that I have to for example, I'm saying that gain is equal to 4. So I mean, it means that I want to increase the amplitude of the received signal by 4 times, which means that I'm putting some power amplifier there. And this power amplifier will take my input weak signal and at an input, and at output, it will increase the output by 4 times. So I'm doing something like that. And I'm saying that out, let's say my other signal is out, is equal to, first I will take the FFT of this one. IFFT, I want to convert it into the time domain again. So FFT is converting it from time domain into frequency domain, and inverse Fourier, fast Fourier transform, or IFFT, is converting it back into time domain, because we want to see the signal exactly in the time domain and compare it with the signal that we had transmitted, right? So IFFT I applied here, and then I am saying that the amplified underscore output is equal to the out multiplied by gain. Right, so I am just multiplying the output with the some scalar number, and let me plot it now. So this is the figure number 11, and the figure number 11 should be firstly that. So I have to plot it in the time domain, so I don't need the f underscore freq anymore. So I already have the time domain signal, which is this one. So how about I just do it with this one, which I defined it in start. So I should say that plot the signal in terms of the t comma, and then I have the amplified output, which is this one, and then I have the comma t comma message signal, which was just this one, and but in the time domain. And then I want to yeah, but I don't have to give the color because it will do it automatically. And then grade on, and then x label is the time domain, and the y label is the received signal versus transmitted signal. And then I should also put the legend here. And then the first one, which is this one, is the received signal. So I should say that the RX signal, and the next one, which is this one, is the TX signal, right? So the TX signal, and let's see how it looks like. Oh, invalid expression. Okay, yeah, it should be in this form. Here we go. So this is the transmitted signal. The red one is the transmitted signal, and the blue one is the received signal. So of course we have some degradation here because of all these processes that happen, but finally we recovered something which is looking like the original signal, and from here we can recover our information because we are not completely skipping some of the whole cycle. We are getting some degradation in terms of amplitude, but the overall pattern looks the same. And there might be a little bit shift in the frequency as well, but still you can see that the blue and red both are looking exactly the same. So this is the final part of the end-to-end communication system, and I hope you understood all the processes starting from the signal generation, sampling, quantization, encoding, transmitting it through the AWGN channel, And then the reverse process, which was demodulation, decoding, and the reconstruction of the signal. So all these processes happen to that signal, and finally we record the signal at with a very little degradation. So this is it for today, and I'll take your question if you have. So please ask if you have any question here. And yeah, today's lab was a little bit tricky. So can you please go through all the code and understand it line by line? And if you have any question with any part, and if you don't understand it very well, just let me know through email with the snapshot of the code, and I will just respond you quickly. Okay, so if you have any question now, you can please ask. And if everything is clear, then yeah, I'll see you in the next lab with a new, we will start with some new things so that we had discussed in the first lab. So we will start with the lab 7. So I think I have received some, do we also have a midterm on the, okay, yeah. So as I, at the beginning, I told you that we will have some portion of the lab included in the midterm. So just go through the code and also the notes that I'm drawing. So please take a look at that one as well, and do understand all the concepts that I'm explaining you during the lab. So it will not be very tricky questions. It will be very basic questions, but at least you should have attempted the lab before when you are doing the midterm exam. So please don't worry about that. Yeah, it will be quite easy for you if you have attempted all the lab assignments. So today I will just upload the recent code. Yeah, I will upload the recent code after this class is finished. So yeah, maybe 3 or 4 minutes after I will upload this code, and also the video of this lecture. So I will upload everything. Okay. So thank you so much. If you don't have any question, then I'll see you in the next lab. Okay. See you. Bye bye.
Thank you.
Thank you. Bye bye. Have a nice day. There was some question by some person. Let me see the attendance once more. Okay, so if someone has the missing attendance, just they can wait and the rest can leave. So the rest who already have no problem with the attendance, they can leave. So let me go to the learn in I don't know where is that one. So the person with the name 1398 is it?
Yes.
Okay, so 1398 is here, and 1496.
Yes.
And okay, let me save this one. And then anyone is absent in the, okay, 1529. 15, okay, 1529 is here, and 1564
Here.
and okay, let me save it. Okay, and the third page there was 1593. 1593. No. And then on the fourth page there was no one. And okay, yeah, I think all done. Okay, thank you. So I already put your attendance. Okay, see you in the next lab. Bye bye.